So first of all, I'm really happy to being back in Berlin. So I was here in the startup scene a couple of years ago, and actually I'm on the way to come back here into Berlin with a couple of friends, building my next startup. And today I wanted to give you some insight from industrial side. Yeah, so that's the arena where machine learning is being applied. Also the energy industry. What kind of problems are we facing? And so I start differently. So I start at the challenges, at the applications we do, and then gonna deep dive. What do we think we need to do in the energy industry to solve it? Yeah. Um, this is, as said, the first thing what I want to share with you, and I may need to explain it a little bit for the non-experts in energy industry. So of course, also energy industry have realized it's quite powerful technique, no? AI and all machine learning models, agentic AI and so forth. And we see here on the green side, these are our main applications we're having. So we're doing predictive performance. We're gonna do autonomous operation. We're gonna do field service optimization, fleet and asset performance optimization. So it might sound new to you, but what the whole thing is about, and may I start that way, Siemens Energy is doing gas turbines, in the future H2 turbines when H2O is available. Then we're gonna do working on solutions for grid technologies, so that Stromnetze, yeah. Wind turbines comes up again, and so we all gonna apply the solutions to this environment, yeah. So that's great to see, and I can tell you that I have stopped counting in Siemens Energy. We have built, I would say, 300, 400 use cases in AI, primarily around these topics. But we're all facing also problems and challenges, which is more on the right side. And let's say still it has a little bit of a lab status, I would say. Yeah, so we build a lab, if you will, on 300 use cases, as said. And the challenges is not necessarily in the energy solutions itself that we could not apply it, but the impact if something goes wrong is quite high. Yeah, so I may give you an example. We have a customer in the Nordics. It's Aker BP, and it's one of the most innovative companies in the energy sector. They really do everything what's on the planet on robotics and machine learning. They work with all the hyperscalers, with all the famous AI companies, and we have not yet found a complete solution. And there's a kind of a mother use case, I would describe it, which is one-button startup. You could imagine this like with a laptop, yeah? You're gonna power on your laptop, and the same is true for, let's say, all these energy plants out there in the North Sea. And it's a highly complex mechanical system where we have, let's say, thousands of sequences to run through before we can shut down or even power up a complete energy plant. And the reason is not because we find this so sexy to shut down and ramp up a power plant in the North Sea. The reason is it has an economical reason, because if we don't need these platforms to produce energy, it costs money. So the goal is to minimize, so to say, such a mega use case. Inside that, we have, I would say, at least 50 different types of applications again on AI, and all need to work. Yeah. So that's here on the right side. If something doesn't work, the consequence is quite massive. So we need to then send teams there in the North Sea, fix it manually again. So whatever accuracy you can bring to us is really important. Yeah. I heard a lot of things about uncertainty. Yeah. You will hear today also about black box models. So we'd like to look at this like, okay, we're going to scale the whole AI use cases once we better understand what's going on inside the models, yeah, which is quite a challenge. So at this point in time, we train the models, we have the accuracy in the lab, but often we see quite significant drifts if it gets to the reality. And this is what the whole presentation is about today. So having said that, is there any way to make the decision paths more visible and to minimize the risk on the real physical world, in this case, the energy plants? Okay, so here again, this is what my boss asked me all day. No? What if we're going to use the whole thing and be in a phase of production stop? Yeah, so we'd like to avoid that and not test it out in the field. Yeah, so to say, this is really urgent. Then it can lead to asset damage. Again, an asset is can be a gas turbine or H2 turbine or wind turbine, which doesn't work anymore. And so there's massive financial risk. And then the safety risk is also not to be underestimated. It also has always something to do with the lives of the people. You could imagine if such a machine breaks, there's also, let's say, some human risk integrated into the same. So that was our motivation. I started that way. Of course, I'm also interested in technology. We come to that, yeah. But as I work for Siemens Energy, that's what they're looking into. If that's being solved, yeah, I always put it in quotes, yeah. So like a provocative statement, is it really solved? Of course not. But we make steps into the same direction. Okay, so let's say we define 3 fields. We call this stability tracking of AI. Yeah, so what can we do to stabilize AI algorithms on the output side, on the classification side? And this is not an easy problem, no? So say, because we need to see that we have not controlled environments. No? In a North Sea environment, as an example, if you're going to get out, let's say, gas of the ocean ground, yeah, that boundary conditions always change, yeah, in minutes, in seconds even. So how you could actually, yeah, apply a machine learning model to it, it's very hard to do. So it's totally different, like in an enterprise environment where you have control conditions as such. Then number 2 is explainable AI. So there's something to be explained in the machine learning models itself. At the moment, let's say that's more being discussed in the agentic layer. Yeah. So, for example, 3 weeks ago, I was in the US talking with Google how they want to solve the problem, and then they're asking, okay, we will build on this, so to say, agent gateways, they call it, control agents is another word for that. And then the idea was, let's say the head of the R&D told me, okay, the idea is the control agents should track the success passes of the real agents doing the job. And I said to him, well, that's great, but who controls the control agent? So there's not a good answer to this, and maybe it's never been solved in a satisfied way, yeah. And we should not expect that. But again, if you map this to the context of energy solutions, we need to be, yeah, we need to move more to a SLA-based AI, service level agreement AI, or at least it's a narrow spread in results, yeah, what we should expect from AI. This is explainable AI. Then contextual AI means we always work in context. So like an example is if you gonna, let's say, run a wind fleet, yeah, and you want to optimize the energy production of the wind park, we have this so-called wake effect. That simply means that we're gonna align the different wind turbines to each other because of the wind flow. And so it's not done that you have an optimization for a wind turbine itself. You need to do this in a fleet, yeah, so to say. Again there, yeah, almost unpredictable, the boundary conditions. So the question is how much more data we need, yeah, in order to get this under control. And I have my belief in it. I'm happy to discuss it with you. It's more like a hypothesis what we are doing, that eventually we are looking into not completely the right things in machine learning. I come to that in a second. Now this is for the CEOs of the company, you know, that this always gives them a feeling we're working structurally along different architecture layers. Like we're gonna do data governance now to, of course, prepare the data as such. Yeah, that's all good. Then we have now defined a so-called model trust layer where we're gonna get the machine learning models even better, like with physics-informed machine learning, etc. but we're also working on a new field, which is uncertainty quantification and how this can be pulled out of machine learning models as such. And to look at uncertainty not as a problem to remove, but a feature to back inject into the learning process. Yeah, this is a different idea, no? And then let's say again for the decisions, we need to make this explainable in some way. This is a very hard field in itself to let's say follow up what's happening inside the neural network or a machine learning model, such that we can say, okay, now safely we're going to shut down the platform, yeah, so to say, as such. Okay, you see, this is let's say the context. This is more for the managers, I would describe it. Now, I wanted to, let's say, raise some topics I was stepping over. So, and I have to say, I'm since I would say 30 years in the field of mathematics and machine learning. So when I was a student in IBM, I first touched on neural networks. Probably most of you were not alive here on this planet. Then I stopped for 10 years doing some other jobs. Then started my academic career, and then I realized, okay, the foundations of all the models have not yet changed. What has changed is the compute power and the ability to test things. And now, let's say, I decided to step into the whole thing again because I think maybe there could be also some alternatives. Let's take it that way. To get into the topics, data reality, yeah, we can do something there. Data contracts, monitoring, remove the noise, etc. But I have to say, no, when I looked in the recent models, one of the basic problems is how you can separate noise from real information. Yeah, if you're gonna do it, let's say we started in image analytics again, and to me, yeah, that sounds a little looked a little bit special. What the community does to there, they try to apply filter technologies, yeah, to then hope that the information is nicely separated from the real noise. I didn't find even a good definition what noise is about, yeah, how you can mathematically, let's say, describe that. And so we're working on that field, and maybe one hint, we started some experimentation here. AJ is one of my friends, which also goes now into the new company. We come to this later. And I was thinking, okay, why doing the things completely differently? So we, let's say, did some tests on so-called periodic networks. Have anybody touch points with periodic neural networks? Not so far? Okay, so the idea, I'll just share the idea a little bit. What's the idea? So today, if you do image analytics, now we have then the encoding of the picture, like in integer numbers, real float numbers, etc. But it's one data scheme, yeah. And then based on this data scheme, you try to separate it statistically often. Yeah? We were hearing the last keynote speaker, they also do it statistically finally. And but if you think about the first question is how you're going to separate mathematically information from noise. Is there a way to do this? And in prime numbers, this is, let's say, as you know from school, you can divide it by the number and by one itself. So naturally, yeah, you can separate in our own mathematical room. Yeah, so to say, as an example. Yeah, I hope that's right. Yeah, so look at me and correct me. And now can we use this principle to separate the picture in a different format, like we describe the image based on prime number scheme, like 1, 2, 3, 5, 7, etc. It's being used then like a filter. Yeah, you get a different picture, but you get a signature out of it. No? So like if you're going to detect the 5 to the prime of 3 and 5, it looks differently, like a representation scheme. So is this an ideal? Yes, it's an ideal, because the information and noise separation is done mathematically and not via afterwards filter techniques. Yeah, it doesn't matter if it's a machine learning model or a mathematical model. This is one field we are looking into. Then the generalization topic. This is a very interesting thing. Let's take the uncertainty principle. So as said, we are at the moment focusing on image data and image data. So you get something presented like an image, you, let's say, have a representation of that. And then, let's say, in a human brain, for example, you have some memory out of it. You saw it once, yeah, and you don't need much of data to, let's say, if you have a small kid, a baby, you're going to show the baby a dog, and then next time you give it, let's say, a label or say this is a dog, and the next time baby can immediately, without further training data set, memorize, so to say, that this is probably a dog, the next picture you show, yeah? So from my point of view, there needs to be like functionality like episodic memory, yeah? You need to build out of the few trainings examples like a representation in episodic memory such that you can back relate this into your machine learning model. So the idea is more like, okay, uncertainty is not a problem. I just have a difference. I'm not 100% sure that this is a dog or so. So why not back inject this as a learning signal into the machine learning model? Yeah. And I give you a practical, now back to the Siemens Energy world. If we got to do processes, like often we have, let's say, 10, 100 feature classes we need to predict and classify. But what if there's a new feature class, yeah? Then because it's not trained for the model, we immediately need to stop the process, and that's definitely wrong. So this is one of the major problems why we don't get this into application. So now if you have this uncertainty signal, and it's consistently coming, no? So it's really something new, yeah? And this can happen. Why not form out a different class out of it? Yeah, yeah. It can be auto-labeled. It needs to be confirmed via some other AI who has the knowledge, or a human, but you don't have to stop the process just because you see something new. So in this case, uncertainty signal is a feature and not a problem. Yeah. So we need to learn, because also the brain works like that. Yeah. You're not getting trained on millions of data classes. The brain completely works differently. And then let's say the brain don't need a lot of training examples, and we can all this by the means of 20 watt in our brain. So something is completely broken. Okay, so I want to motivate you now to go a little bit into a different direction. Now, having said that, black box models, no? So I also, we can discuss a lot of things, but what I never understood is, let's say when we have such a topology, and at some point you need to select the activation functions, right? For separability of the data sets and so on. What is the mathematical criteria why you choose the one or the other or different one? So I didn't find any good paper to say, okay, these are the criteria why you choose the activation function in your topology this or that way. Does this make sense? So I'm not sure if there's any research going on, but we also did some work there. And what we did, like a simple example, we took the complexity of an image, right, to derive, so to say, what's the complexity in the picture. Because the complexity means something to the activation function. Yeah, so we make it dependent now. And I'm going to show you later on some results, how good this works. But, you know, from my motivational talk is about, can you please also look into the mathematics, why we got to select activation functions in this or that way, just as one example of many, many issues we still have in the machine learning. So today, to me, it looks a little bit empiric. No? The people often say, but it works. But why does it work? If you don't care why does it work, you have no idea why it doesn't work afterwards also. Okay, uncertainty I already talked about, energy efficiency. Maybe I scope the problem again. So at the moment, the hyperscalers and all their models, including the transformers, are going to go for brute force learning. Yeah, that's extremely exciting what the output is about. Yeah, it's extremely impressive. But if you think about a problem, let's say I heard yesterday something when I get a 200 euro codex license. Yeah, at the moment it's being funded with multiple thousand euros. Yeah. So to say what I can use, that's great for me, but at some point it will change, yeah? So it's heavily overfunded, so to say, yeah? So it's more like to attract the people to come into this model. The real problem is they should build energy efficient model. Think again, the human brain can do all the job with 20 watts. It's the best generalization engine on the planet still. And they use, let's say, the energy consumption of New York City just to train one model for the next release. Yeah, this is, from my point of view, not the way to go. And so let's say if we look later on into the architecture, you will see what we do. I built a simulation maybe before I go there. This is the way the energy industry is doing today. Yeah, we help ourselves, but finally what we do is we're going to believe the black box model and build stuff around it, such that how can we detect if the models are going out of scope, no? Or out of the expected. Yeah. So for example, here in the middle, you see the expected operations. No? There's some data, and then if it goes outside of the circles and the intersections, we know, okay, it's going outside. But to be honest, it's more or less, let's say, afterwards correction of the things we don't really understand. There was a, let's say, discussion, and we are really a time series industry. Yeah, so we are doing everything about time series. We have thousands of sensors on gas turbines, grid networks, etc., to collect the data. And from my point of view, now talking as a mathematician, whoever has tested the probability distribution of the time series before he did the regression? Anybody? Yeah, very good. I'm gonna hire you immediately. Yeah. So this is, you know, we cannot just do linear regressions because sometimes we need to look what the probability distribution is underneath. For example, in Cauchy or Levy distributions, you have open-ended. So how would you calculate there's something? It's not allowed mathematically, yeah, because the average values are not existent. It's infinite. So these are, let's say, some of the problems I wanted to highlight, yeah, so that we also go back to the roots again, to really think about what is the reason for that, how can we deal with that? And this is the consequence. Now we try to look at the signals. Often it's aggregated signals to find out, is there now a problem, yes or no? But if you don't fix the mathematics, it's getting difficult over time, yeah? There's some new fields at the moment, like extreme value mathematics. So it helps, yeah, but there's active research to do. I'm going to go to the next slide now. Okay, now let's go a little bit into what we want to do differently. So these are the 5 categories we going to look into it right now. So the one is about robustness, yeah. How can we deal with uncertainty in noisy data because it changes? Yeah, we cannot train our models for every change in the data again and again and again. Think about weather conditions in the North Sea when we do, let's say, alignment of the wind turbines. This is something the model ideally itself should capture. Yeah, it's a big dream, but on the other side, it's not an option for us, yeah, to retrain the model every day. So say just with continuous data, etc., and you still don't know mathematically if it works. Then glassbox means that we're gonna, let's say, want to understand how inside the model thinks itself. Yeah, so to say, what are the decision passes, what's being used, what's not in a neural network, and to get an idea how was the decision path internally to get to a conclusion. I always take this example of from the medical side. Yeah, so if you look at the cancer picture, yeah, let's say it's like a picture where the body is scanned and there's a likelihood to have cancer, you rather want to know before you get the prediction that you have cancer that it's really safe, yeah, so to say, and not just a false positive, yeah. So that means the model itself needs to get better. Then let's say one size fits all model. No? So yeah, that's what maybe now sounds conflicting. Yeah, is there let's say a model which can solve all of the problems? Of course not. But maybe another way to look at this is okay, can you have a model which is self-adapting? So it auto-generates itself, yeah, such that it fits to the input problem. Yeah, this is another way to think about it. And you rather find the principles in order to do so. Yeah, you still have a variation of models, but you have the principle to auto-generate a model. Yeah, and I'm going to show it in a couple of minutes about that. And then let's say drift detection is another one. So when do we see that the model runs out of range, no? So to say, it just doesn't do what it was trained for beforehand? And is there a mechanism that we can autocorrect the drift detection in the topology of the neural network itself? Yeah. Okay. So going a little bit down, I can also not step through all of these things, but from left, let's say how we're gonna attack the problem, like for robustness of observable, for glass box verifiable, for not one size fits all adaptive, no, etc. So it's all, let's say, from stable inference into gated, drift detection into control. I'm gonna make for everything one example. So does anybody know Spencer Brown? He's a very famous mathematician from the UK. Yeah. He says, okay, he did a lot of research in formal mathematics, and at his later years, he tried to attack the so-called consciousness problem, yeah? And came up with a very simple definition. If you have a piece of paper and you can divide that area in two different areas, that's the start of consciousness, so to say. Yeah, think about it. No? So you need to have some reflection such that you can do this. Now, a question going back to machine learning: can we use such a principle for example, better separability, you know, in activation functions? Yes, you can. And so this is one of the concepts we are working on. Yeah. Then on the, let's say, on the episodic memory. Yeah. I heard very closely to this, let's say, statistical approach from this tabular AI. We're doing something similar. So let's say after the input picture is being read, we're going to completely transform this into signatures as well. So to say that we can have a kind of an identification of the representation through our various layers. Yeah. So, and the one thing is, if you're gonna, let's say, have a normal CNN, but let's say our approach is slightly different. We look heavily into so-called frequency patterns. Yeah. A frequency pattern, think about an input picture like this one. Yeah. You have your blue zones, you have white zones, you have very similar zones like in this purple in the background. So mathematical resonance comes in place when, let's say we say in physics, when the particles swings with each other, there's a resonance, yeah. And for image analytics, you could do the following: say, wait, you can have similar colored pictures, like this is a resonant pattern, and then the opposite is of course then have the ability to detect edges as such. And then you have a general language, because you don't need to, let's say, look into, so to say, the, like in acoustic, yeah, you can also have a resonance, so to say, in overlaying frequencies, so to say. So why is this? Because we want to, let's say, if we want to build modular architectures in machine learning, yeah, we need to find a kind of a way to translate between these different layers, independent on what the input data is about. Yeah, so say if you have an acoustic problem, then you're going to turn this into this resonance model. If you have an image problem, let's say pixel data, you're going to turn this into this resonance model. And then you can aggregate the two patterns into each other. Yeah, so that's our idea on this, on how to do it internally a little bit different. Okay, long story short, I can talk to you whatever I want, no? If the things does improve. At the moment, we are having tested last 2 months or so 2 data sets. Of course, it's not enough. Yeah, we need to do more. But I can tell you, with the latest model we have, we named this Koch-Scholze tower. I get to this in a second, what Mr. Scholze is about. We have tested MNIST. We think we are very advanced, even if it's a super simple data set, like this is pattern number recognition. No? It looks easy, but it's actually not so easy to get to the 99 and 100%. So I think we are very advanced on this here. Yeah, so there's a, you call it leadership board. Yeah, I learned. Yeah, and then the last thing I was seeing was 99.7.9. We are now on 99.8 now. But the important point is at 33 epochs, where all the other needs hundreds. So the cybernetic networks, what we call it, seems to work. And here, this kept me up at night, so to say. So I learned, first I was approaching this data set, this is easy, but now we are in CFAR10, which is a very noisy data set, probably you know it. It's a very low resolution data set with different kind of pictures, which even a human cannot really recognize. We are now at 97.8. Yeah? The second one is 97.5 something. So I think it works as a principle. And here again, let's say the amount of epochs was 380, where others had 1,000, 1,500, and 1,800. So some truth is in so it still needs to be verified. I have to say, as a good researcher, I need to do more proof points. But at least it gives me hope, so to say, that this is the way to combine energy efficiency with accuracy and dealing with noisy data, so to say. Yeah. So it's not representative. Don't run out and say, God, and this company has solved it. We need to do more verifications. But the first test looks very promising. Okay, now I'm going to show you one thing. I hope it works. Yeah, you see here two simulations, one on MNIST and the other one on CFAR10. The important thing is what's boxed here. And it runs through and runs through. So let's say you see here, so let's say horizontally mapped all the layers it could use. But finally, the cybernetic networks with this back injection of uncertainty model have decided to use here layer 3 and 4 and look at this. Here on the different data sets, it uses different layers. And this is the last feature we are working on. We're gonna, let's say, detect on the input complexity of the picture how deep the network needs to be. Yeah? So say, like, if there's a certain entropy, yeah, if entropy is very low, yeah, then it's a different thing if entropy is very high. So why should the network take the full capacity? You also don't do this in your human brain. You take what's needed, so to say. And this is, let's say, a simple simulation which actually convinced an investor because it opens the door in more energy efficient networks. Yeah, eventually you don't need the full capacity at all. So this simple test shows you, okay, and it runs from the beginning again. So now it has, decided to work on layer 0 is the first, 1, 2, 3, and 3 and 4. And for every, let's say, data set and picture is of course different. So now think about it. Is there more, let's say, what we can do on the energy efficiency? The results proves it at the moment, that let's say HAU said 3.5 times better what the comparable model will do. And again, I need more verification, but it looks like that it's very energy efficient. So it's a dynamical structure in the topology itself as well. Don't scramble this with a classical CNN structure. It's built on top of it. Yeah, and then the final step will be, is CNN models needed at all? Yeah, because you can also eventually do it in the future in the memory, like with this resonance model. So to say, it's a very static model. CNN, yeah, it's fixed. A topology is being chosen, an activation function is being chosen, but that's not the way the human brain works. Obviously, it's dynamic. It chooses the connection, what it needs to solve a problem. So we're starting to work on this principle further. Here you see a small red box. It's almost not seeable, but there's another thing into it. It's also based on uncertainty. When you have a certain level of uncertainty in the network, so why should the network then classify? It should not. Either it should abstain or it should learn more. And once it learned more and it's safe enough, then it should classify. And the next level is that we have a self-observation of the network itself, so to say, such that it's in a stable inner state. So what does it mean? Let's say I'm coming from mathematically from the field of dynamical system. You need to understand if the eigenvalues of the whole network are good enough, such that it's not deconverging, as such. So this is inner state of the network. And just if the eigenvalues are good enough, plus it has a good learning curve, then it's being classified. In the other case, it's being abstained or needs to observe more. So I hope this makes sense for you. So it's a completely different approach. We allow the network to be uncertain. We don't see this as a problem. The problem is if you're gonna decide too fast. Again, back to the Siemens Energy world. If we would have 10 failure classes on a gas turbine, and based on the 10 failure classes, we would decide to either let it run or let's say shut it off. And we see 11, problem number 11. Today's network will just decide inside the 10 failure classes what they think is best. And then we have the biggest problem on our side. So that's something we cannot accept as an energy company. Okay, so it definitely makes sense. Now here are some use cases that you see. Of course, we're also working on all different things. This is at the moment most popular. We gotta have drones which are moving around in the energy plant. But again, here, we need to deal with uncertainty. So to say in a ocean ground, where robots are going, like we have this ocean ground robots where they try to detect the field pressures, etc. It's changing every second. So far, we have not one model where we can say this works sustainable. So there's the biggest need probably there. Then we have the topic of cybercritical infrastructure protection. That's more or less we're looking into drones, how to protect the whole systems, etc. Asset performance management is our classical use case, I would say. Again, asset is a wind turbine as an example. So we put sensors for ultrasound, vibration, actuators, anomalies, etc., time series analytics. Now, which sensor you should believe? The best is you have an integrated picture of the same, And there's a lot of work to do such that you can classify, okay, the wind turbine now needs to be taken into maintenance or not. So the isolated classification doesn't help us at all. So we now opened up a new direction, which is called behavioral analytics of the asset. So we take more things into context. The context is, for example, out of the sensors, and then out of the contextualized prediction, so to say, then we can decide if we take it off or not. AI agents is also one. This is, let's say, of course, the goal is in this example of one button startup to have one autonomous operation. So we will have many, many agents working together. But I have to say, we also need to fix the basics in the machine learning models. Then we can go upwards. Then we need to fix the next problem, which I told you, which is the control agent problem, who controls the control agent, etc. So finally, I'm not sure where it's going, but what I also know, if you have a bad foundation, you should not piggyback many things on top of it because it has just too much impact in our energy infrastructure. Okay, so then here you see, because it's a very traditional industry, not everything has something to do with AI. This is how we're gonna operate today. This energy plant, we call it plant automation. It's not yet plant automation, of course. It's a mix of classical and new techniques. At the moment, the hope is at least that we can automate processes, so such that you can type in a prompt and then get the facial picture of turbine 1 to 10 in the North Sea, and it's automatically dashboard. That all works, but we are heavily working on the trustworthiness of the AI also. Can you really trust the result? Which is then relevant for our insurance agreements with insurance companies, etc. Okay, then here a little bit for the people who like pictures. So we built out now, let's say, a kind of architecture, how we would operate the whole thing. middle layer we are actually working on, right? Like what is the foundation, so to say, for operating energy environments, no? Like we have a layer for industrial knowledge graph, yeah, so we need to model what's in a system. We need to also model the interdependencies of the same. And it was a surprise to me to see that companies like Palantir already, let's say, stepping into our business to do exactly that one, yeah, to model the ontologies between the assets, you name it. And but here on the right side, like let's say version 1 of this adaptability, yeah, that's like I always say with the hand at the arm solution that we have a AI lifecycle model. So if we see there's a model drift, we rather exchange the model because it's not working to the expected. No? So for every machine learning model, we have a control model meanwhile. And then with the control model, we see is there is a drift, and then gonna exchange the algorithms on the fly, yeah, which is not always easy to do because of the second problem. Machine learning models today like to classify. Yeah, let's say Elon Musk said at some point, let's say there's no model on the planet right now which can say no or I don't know. Yeah, type something in a large language model and you always get an answer even if there's no answer available. Yeah, and then on Monday you get a different answer than on Tuesday. So that's not really helpful. Yeah, for us. Okay. Anyhow, if this is being solved and take it also like a motivational talk that you change your research direction into these fields like explainable AI, stability tracking, contextual AI to go for the next level. So I think we have many models today. It's based on the today's knowledge of mathematics. Yeah, that's all great, but also mathematics has limitation. Yeah, yeah. So it's a and but we hope to get something out of it. There's here a big number which we hope to achieve. 500 billion cost reductions is our energy processes. I have to say I'm optimistic, but not so optimistic. No? We need more research moving forward. Before I end, I'd like to mention one guy which you might want to have a look at it. He teaches at the university in Bonn, Peter Scholze. Yeah, I'm not sure who knows him. Anybody knowing him? Yeah. Oh, okay, super. Yeah. Peter Scholze is really doing great work to bridge the different fields of mathematics. We also did some tests in our own environment, like this, we call this, if you don't know the names, don't worry. No? You will find these carbon lifts and perfectoid rooms. It's really a cool environment because this is one of the way to get it mathematically precise. Yeah? I do want to be friendly to the statisticians, but I often say when you need to put it into the statistics, you're going to put it into a field of mathematics you just don't know enough about. Yeah, and I recommend you to have a look at Peter's work. Yeah, he's really unbelievable, cool guy. It's also super abstract, but we already can see that we can derive some applications out of it. So, for example, you can use it for generating noisy and noise-free synthetic data. Yeah, if you move it into these different dimensions, and the foundation is periodic numbers again, right? Okay, long story short, so this triggered me to do something, to step into the field again, yeah? So it's now the third time that I go into AI. We already started our own company. Now, Syndromind AI, you might want to have a look. It takes care about industrial stable processes with the help of AI and all machine learning models around. And yeah, maybe also in the next couple of months, we're also looking for new employees. Thank you.
Yes, thank you very much, Gerhard, for your very interesting talk. And I think those two are actually directions which are super promising. And we hope really that you make advance, right? Because we really need that less energy consumption and more reliability. So Are there any questions? And I would suggest that Gerhard chooses people.
Okay. So in one of the first slides, you mentioned self-supervised learning and joint embedding architectures. So I was wondering what kind of real-world data is Siemens trying to embed in the latent space, and how is it trying to align it? If you can answer this question, I don't know if it's...
Can you repeat the last?
So what kind of data are you trying to embed and align with joint embedding architectures?
Yeah, so it's... Let's say our company is pretty much 90% time series data as of now, but this is going further, right? So self-supervised learning is not just in the classical sense like having, let's say, a label for data set, yeah, and then you're going to say, yeah, bad or good or not so good, yeah, that you're going to classify it on that path. The self-supervised learning, my definition is, and maybe I have a different definition like the community, is that you have a model which will generate the data out of the model itself to self-observe. Yeah. So if the model is in I talked about this eigenvalue state. Yeah, eigenvalue is if an eigenvalue is smaller than 1, yeah, or close by 1, it's stable. If it's going above, it's getting unstable, yeah. And then, let's say, if you are operating in such a neural network and you have a mathematical approach to detect the stability, which is the eigenvalue, yeah, so to say, then you can classify. So this is data which comes out of the learning process, yeah, and then it's being put into a second model which observes the learning process itself. So it's so that's the best way I can answer it. And then if you're in a good state, yeah, like if you're fit as a person, yeah, your eigenvalues are good this morning, yeah, so you're stable, you had breakfast, this and that, yeah, then you are allowed to classify. This makes the model even more stable, yeah. So we're going to self-observe the machine learning network itself, yeah. So it's like a self-observing of what's going on in the learning cycle, yeah, so to say. We continuously calculate that, yeah. So that's my definition of self-supervised. Yeah.
It's mainly time series data that you're trying to get information from.
You actually you can apply to any kind of data. No? For every system, you can calculate eigenvalue models, no? So to say, like to let's say make a even better improved stability of the model. No? You can do it very classically that you can say you can, let's say, detect the probability distributions all the time, but it also got some compute power, yeah, to detect if you're allowed to calculate at all. We have chosen the path of eigenvalues, no? So that you have a continuous measurement of the stability of the model itself. Yeah.
Thanks.
On the slide regarding the model architecture, you said that the model's, let's call it effort, is influenced by the input entropy, if I remember correctly. And I was wondering how that works specifically and whether you've explored a different method, maybe using the model regressively, like if the model says it's very uncertain, then maybe it should put in more compute effort and try again.
Yeah. Okay, so okay, that's one way to do it. So let me first explain the principle. The principle is you're gonna take into, let's say, the way the network calculates what's coming in. No? So say it needs to have an impact. If you have a simple picture or a complex picture, you need more brain power to find out where the objects are with your brain. No? So the same principle applies there. Now, if you take entropy, now this is a very global parameter, yeah? Or you're gonna do it more structured, yeah? That you have, let's say, an understanding of local patterns and local structures in a picture. So you can also have like order, let's say, a structure vector, like later on, and replace the entropy with it. For me, it was just important, is there an effect, no? you should take in a complexity of the outside world, like in this case, image, and we measure that with entropy to make a mathematical function to detect the deepness of the networks. That's what you saw in the, or what you see here. No? So the more complex it is, the deeper it goes, the more compute power eventually is being needed. Yeah, and then if it's a simple picture like a number, that's not so complex to detect. The structures are clear. The entropy is low, as we say, but you can granularize that also. Yeah, for me, it's more the principle important. Like as an example, entropy triggers the deepness of the network. Yeah, but you can also define it differently, of course. Yeah, with some. It's more like the input. What does input mean to how a network is being constituted? That's the principle. Yeah, for me, it's more the principle. You can also define that differently. Yeah, that helps. Yeah.
Thank you. Thank you very much.
Yeah, I have a question. Like, so if you say like you turn off like some layers and some stuff like that, and you calculate all these things, are you doing that on a per image base, or like do you like do like for specialized AI that you have like basically this kind of set? We take the cross entropy of that set, and we say, okay, we need not the complexity, because for me that was unclear.
Yeah, we started at the batch level. Yeah, so to say, like multiple pictures together, if you will. We have not yet tested on individual images, no? Because it eventually makes sense or not. Yeah, we need to see. Because if it's a movie, no, and it's a standing, yeah, you have let's say static situations, no, then on any picture doesn't make sense. You would counter the effect of energy efficiency, but if you have a lot of changes in a background, as an example, then it's worthwhile to think about even image-wise. Yeah. Again, it's more like the principle. Yeah. At the moment, we test it on batch level, and it has an effect. No, so say such that we use this entropy on the input of the picture to adapt the activation functions accordingly. No, so that the complexity has an impact to the separability in the activation function. Yeah, that's a implementation we have right now, but nothing speaks in theory against to do it also image, yeah, per image. It can be done, but for that I didn't have the hardware to do so. Yeah, so I needed to compromise on the batch level. Yeah.
Okay. So I have a question. As a mathematician, you mentioned quite a number of times we need to fix sort of the mathematical foundations and so on. And so what I'm curious about, do you sort of have like a list of mathematical problems where you would say these would be important to be tackled to go ahead? Like sort of like the millennium problems, something in that thing where you can say like, for AI in the future, these are the kind of questions we need to be solved.
So what's on my mind? Because I'm not so, let's say, long back in the machine learning scene, just 6-9 months, I test around for myself. Yeah, I have the same background like you. So on my wish list would be if somebody can explain the convergence of whatever machine learning model and why that is, under what criteria. Yeah, so I come from the arena of swarm networks. Yeah, there you can define convergence of a swarm as an example. Yeah, it's not so far away of the machine learning models. And then somebody needs to understand, let's say, how you're going to define the convergence, how you're going to calculate it, and what boundaries it stays stable. Yeah, as an example, that would be one of my things on the wish list, that somebody can explain every topology and how it converges. I know it's a super hard problem, yeah, and so people need to sit down under what conditions, yeah. So that's more like a system convergence, yeah. I'm not talking about the classification part. I'm talking about if a system converges bad as such, it's very unlikely that you could get good accuracy results as such, yeah. So that would be my main topic, no? That's also where I'm expert, I would say, yeah.
Just a follow-up question to what you just said. Are you familiar with like the Webnick-Channevankis theory on like statistical learning theory and the complexity measurements that they are doing?
I have looked at this, and yeah, I think there's a lot of truth there as well. What I'm still fighting a little bit, sorry if I say that so direct, is machine learning as a statistical discipline as of now. So say there's a lot of statistic inside. Let's say there are many things like gradient search, calculating gradients, and my question to the community would be, why do we calculate gradients in a statistical problem? It might work, yeah. But let's say if maybe I'm totally blank now again, so looking at the problems differently than you are, which are into the topics, why don't you take methodologies like from Peter Scholze, yeah, like on perfect rooms to solve it differently? Because it's not super clear to me, yeah. So let's say all these statistics I'm observing, it has, let's say, made good progress, but we all know there's a lot of things which cannot be solved there. Yeah, so we park it somehow there. So let's say I think the job is also to look into new fields of mathematics now, like what I tried to describe with this information noise separation. Yeah, we naturally take integer numbers, real numbers forever. Yeah, because nobody challenged it. But if you think about, why do you, let's say, try to find patterns in floating numbers? For me, as a mathematician, it doesn't make sense. For me, the first question is, what's the layer where I can separate the best? On prime number schemes, as an example, you can separate best because it's an isolated mathematical room. Yeah, prime numbers, the number and divide by itself. So if you're gonna pick it at your let's say approaches there, it works much different. Yeah.
I'm gonna stop because otherwise it takes too long. But the theory is all about like separation and how to measure the separation capability of models based on like the empirical risk that you can measure from the data, and how you can make, based on the separation capabilities, a connection between the convergence of the real risk based on the empirical risk. And that's like the whole theory, and it's like very unknown, so that's why I asked.
We can discuss offline. I'm interested into it. I don't know it in detail. I've heard about it. My thinking model was more or less, why statistics at all, and why can we transform the problem into a different mathematical space? Okay.
Yeah, let's one more question.
I have more of an implementation questions. I'm coming from the semiconductor side, and we're talking a lot of edge AI. It seems that these models are quite a system of different models still being tested on servers, basically. Do you see any application, any use cases of edge AI in this context, like optimizing, like because of bandwidth problems or latency problems, for instance?
Yeah, we have a first customer, I have to say, where we do metal part inspection on the fly. That's the one use case, right? Like we classify metal parts. They do, the customer does polishing machines on metal parts, screws, whatever, yeah? And that's the one. And then, let's say we work on a second use case, which takes, let's say, image to predict, so the machine parameters, how, so before the part is being processed, so they don't need to test out, so to say, the machine parameters anymore. So the machine is set up on the fly, So yes, we see this primarily. That's why the reason why we are starting in the industrial side. Primarily edge cases. Our models are also not such big, So let's say we have a model between 12 and 30 million parameters max, so that suited to run at the edge naturally. And as the model has some capability to change itself, our code is not the model just itself. It's more like that we don't need to stop the process, because stopping the process is a catastrophe in manufacturing, because of a new problem which appears, which you need to retrain again. So that's not really an option, for us, But edge is the 90% case, I would say. We thought about energy efficiency to approach Google, but that's too early.